Okay, so as part of their final project in AP Statistics, Christina and Rachel randomly selected 18 rolls of a generic brand of toilet paper to measure how well this brand of toilet paper could absorb water. To do this, they poured 1/4 cup of water onto a hard surface and counted how many squares of toilet paper it took to completely absorb the water. Here are the results from the 18 rolls. 29 to 20 and so forth. So construct and interpret a 99% confidence interval for mu, which is the true mean number of squares of generic toilet paper needed to absorb 1/4 cup of water. Okay, so essentially our goal is to figure out about how many squares of this generic toilet paper we're going to need to absorb 1/4 cup of water. So we're going to start with our statement. We want to estimate the true mean number mu of generic squares of this toilet paper needed to absorb 1/4 cup of water with 99% confidence level. Next, we're going to state what our plan is. So our plan is we're going to use a one sample t interval if the conditions are met. So one sample t interval, and we're going to use it for mu. So one sample t interval for mu. So we're going to check the random condition, 10%, and the normal large sample condition. So the random condition, that is met because it says that they randomly selected 18 rolls of toilet paper. 10%, so they took 18 rolls, so then basically we're going to say that it's pretty reasonable to say there's 180 rolls in the population. 10 times 18 is 180. So that checks out. And now it's normal large sample condition. So the normal large sample condition, we have to have a sample size of at least 30, or the population has to be told to us that it's going to be approximately normal. None of those are met, so then we have to look at the sample size or sample data distribution. We have to look at what the distribution of those 18 rolls of toilet paper look like, since it's less than 30. So we're gonna make. I usually advise making a dot plot, or a box plot. Dot plot, box plot doesn't really matter. I usually like doing dot plots or box plots. So we're gonna go to box plots. So I already entered the 18 values in my calculator here. Then I'm gonna go to my stat plot function. So I'm gonna press second and then Y. I'm gonna get to this screen, and then all my graphs are off except for one. So I'm gonna use plot one, and I'm gonna select this box plot here. You see this one has those dots. That means that this box plot will show the outliers at separate points or stars versus this one. This one won't show them as separate stars or dots, or in other words, disconnected dots. I would always go with this one. So I'm going to press enter on that. I'm going to use the data from list 1. Frequency will stay 1. I'll just use these open squares. Press zoom. Go down to zoom stat. Press enter. And there we go. And that looks, that looks all right. There's no strong skewness or outliers. I can even trace this. Press trace to see what the values are. Minimum 20, Q1 23, median 25, Q3 27. Did I say Q3? I mean Q1. Q1 is 23, Q2 is 25, or the median is 25, 27, and then 29 is the max. So we'll just draw a sketch. You don't necessarily have to draw a perfect, drawing of your box plot, but the better it looks, the more the more knowledgeable you're going to seem, the more you're going to seem what you're talking about. So here's my box plot, and since again I put it in words, this box plot doesn't show any strong skewness or outliers, it's going to be safe to use the T procedures. Okay, so our do part. So we're going to need to first figure out what degrees of freedom we're going to have to use for this sample. So we have 18 rolls, so our n is 18. So our degrees of freedom is going to be 17, n minus 1, and we're going to look for the t star value for a 99% confidence interval with degrees of freedom of 17. So we're going to go to our table B, Degrees of freedom, 17. And this one already says like what comps level you want. So we're going to go to this column over here. So 17. And we're going to use 2.898. That'll be 2.898 will be our T-star value. Now, the form of our one sample T interval will be, I want to give away the whole answer, so will be our samples mean, so x bar plus or minus T star times the sample standard deviation divided by the square root of n, so divided by the square root of our sample size. So I need to figure out what our sample mean is and our sample standard deviation. So I already have the data in my calculator, so I just have to run a one variable analysis. So I'm going to go back to stat, and then scroll over the calc, and I'm using one variable statistics. Press enter there, and I'm going to type L1 just to show that I'm going to run the statistics for the data in list 1. Press enter, and it gives me all my statistics. So I have my mean, 24.94, and you were given the sample standard deviation, and you're also given sigma sub x, which is the population standard deviation. So these are going to be different because remember, sigma is used when to represent when we're talking about the population. But this is a sample, so we're going to use this value s sub x. These actually divide by different values. This one divides by n minus 1, and this one divides by n. So that's why you get slightly different values for your standard deviation. And I don't really need anything else of that, so I plug those in. Just make sure you do the calculation correctly. So 2.898 times or 2.86 approximately. And your sample mean was 24.94. Plug all that. I just use my calculator. 2.898. Now, when you're gonna punch all that in your calculator, make sure you use the parentheses correctly around. If you're gonna take the square root like straight up, just use the parentheses correctly. I have my T star times all this is grouped 2.86 over the square root of 18 that I have in parentheses. That way, it'll give me my my margin of error that I'm gonna add to my 24.94, about 1.95. And then when I add and subtract that from 24.94. I should get right about 22.99 and 26.89 as my upper bound. Okay, so then basically I just go to my conclusion. I say that about 99% confident that this interval captures the true mean number of squares of the toilet paper that's needed to absorb 1/4 cup of water. And that's it.